Okay, chemistry. Yeah, today we're going to talk about models of the atom. The atom. Spell it different from how I spelled it. There we go. The atom. What does the word atom mean? You should have learned from your text. It comes from the Greek word a, well, alpha, which was pronounced a. Is this right? Two words in Greek. A, tomos. In your text, what that means. You would Latinize that as, yeah, which is obviously from that we get the atom. But what does it mean? This means something. Your text told you what is in Greek. That is the letter alpha, yes. But what's the prefix a mean? No. Like, asexual reproduction is special because it is reproduction. How is asexual reproduction different from sexual reproduction? So, no. It's without, or can't, or doesn't, or but kind of so this a in the same way that we yeah, not tomos. What's tomos mean? You don't know because you refused to look it up in your book, even though I'm trying to tell you to. This means unable to. This means not, and then the tomos means cut. You can't cut it. This is related to the word, like a CT scan. The T in CT scan stands for. In a real way, this means you can't slice it. Atomos means you can't slice it. Idea. To him, it was more or less an idea, and he named the idea. And who was that? No? No? Democritus. Understand it. Not study. Effectively, dude was cutting something, and he thought, wouldn't it be neat if there was something so small you couldn't cut it? And that was the extent of his idea, really, and he named that idea, you can't cut it. So that's not really for the time. And did he have evidence for this? This is one of your chapter. He named this thing the atom, and then it was more or less kind of forgotten in history for a while. Because Aristotle of nature that completely unrelated to this. Aristotle had this idea that air in various combinations and in various manifestations makes up everything. Was Aristotle's idea, which had for a long time, really, from the Democritus, which I think your book attributes him to sometime around 500 BCE, and then Aristotle. Everyone's like, yeah, Aristotle sounds for everything to be made out of earth and fire and water and air. So we'll just go along with that until the 1700s. So for 2,000 years, everyone was like, yeah, Aristotle seems right. That seems okay. No one the way human beings. Really, in a very real sense, it was more like, do I think about the nature of matter philosophically, or do I milk the cow so my children don't starve to death? It was, for most of human history, that was obviously not that specific case, but you didn't do a whole lot of this kind of thinking. You didn't do a whole lot of this kind of schooling because you die. If you did, you would starve to death. Until, I guess, really humanity improved on a general level, that someone later came along, Dalton, who really did have evidence for his. Or was it Dalton or Thomson? Don't let me get this wrong. I believe it was Dalton, yeah. So Dalton did experiments that had to do with ratios of chemical compositions, chemical reactions. Ratios of chemical reactants. Kind of like, and this would be a very basic version of it, but kind of like if you mix of baking soda with a certain amount of vinegar, enough to get an exact reaction, what we call stoichiometry. He did that kind of. His data was based on experiments, so already better than Democritus' idea, but it also completely refuted what Aristotle had said. Now, and we had started to understand that there are chemical elements. on the periodic table were what the world was actually made out of, and they had these certain ratios that led Dalton to, and clear, it was not Dalton who said these are the chemical elements. Lavoisier and Priestley and people like them had done this work to show that there are chemical elements that cannot be broken down any further, and they named them these things, starting with things like mercury and gold and silver, which had been known since antiquity, but were still then thought to be fire and water and air. But Dalton's real work was that he showed, using ratios, that these things combined with specific amounts that at least his experiments showed, that only happened if there were some indivisible quantum particle, if there was some kind of particle that made up the element, made them different, but could not itself be divided. So he recoined the term, taking it from Democritus's idea. So Dalton, there were, and people, including me, sometimes say that his idea was just a solid ball of one particular element. Like this one might be, I don't know, at the time he might have talked about mercury. Maybe this and this other ball, indivisible, atomos, indivisible, atomos, but not solid. And he had these different kinds of balls. That was the atomic model. And we don't really even usually call this a model because it's an idea.
Is that a G?
It doesn't really matter. It's a G. It's for mercury. And then after that, various experiments were done as we went along. The first one, using the ray tube, showed that there must be, and the book goes into detail about how these experiments occurred. It talks about the cathode ray tube, it talks about the oil drop experiment, it talks about Rutherford's gold foil experiment, but there were successive, there's kind of a lineage here of the atom as a solid ball, then to Thomson's, what we sometimes call plum pudding model. Electrons were basically. There was the cathode ray experiment that there are electrically charged particles that make up atoms. A cathode ray tube, CRT, you ever see those great big TVs? Like your grandparents had, probably not even your parents, but your grandparents had TVs such as like this, and it would have like this big old box on the back of it, and all these vents, and this super heavy, and this is like this is the size of you, and you have to have 9 friends carry it. Yeah. This was called a CRT TV, which stands for. And what a cathode ray tube did was it was able to take matter and strip off the electrons, and then it was shown that those beam, the cathode ray, this is really simplified, but it's getting the point across, was attracted to, a positive charge, which means that this must be what charge? The tube itself, or the ray itself, must be negative. So it showed that the atom is fundamentally composed of at least some electronegative particles, but we also knew it would be negatively electrically charged, otherwise every single piece of matter would be attracted to a positive electrical charge, and we knew that wasn't the case. So the plum pudding is where those negatively charged chunks would be stripped off in the cathode ray experiment. It was a good hypothesis, met the data that was provided by this kind of experiment. We call it the plum pudding model because in England especially, ish stuff like a soft squishy cake with plums in it. That's not super familiar to Americans, so I sometimes call it chocolate chip model, like it looks like a chocolate chip cookie, where there's a cookie that's positive chocolate chip. Distinct charges here, but that's it. They're within the same still sphere. So what do we call it when science builds on itself like this? This wasn't really science, but we had these experiments that showed there are distinct ratios by which they combine. Then we show, what's that property of science that we call it? Science is iterative, which means that we build off of previous things. We're always building on the previous. No one just completely works by themselves. We're always building off of previous experiments from other people. I'm going to erase Dalton's model, and we're going to move on to the next one. Experiments after this one, specifically Rutherford's experiments, showed with his gold foil, basically he had a piece of gold foil here that was able to detect collisions. This little stuff I drew down here, this looks like a sword. It's not. It's supposed to be, this is a piece of gold foil from the side. This is a little detector. And he had a detector all the way around it too. And then he had an alpha emitter. This would be alpha particles. We're coming up with this. Excuse me. And then actually the detector was connected to the ring around it. And this was just gold foil hanging out. But the alpha particles, if they were true, we would expect the positively charged alpha particles. Remember, because the alpha particles have a positive charge. Yeah, +2 charge. But we would expect that these positive particles would all bounce straight back into the receiver or into the emitter of the alpha particles, or maybe it would deflect a few of them out to the sides. Like maybe they'd bounce, like, you know, if you were shooting basically balls at a wall of balls, many of them would be on this side of it though. But what he actually discovered, most of them, the vast majority of them just passed. So his experiment showed that most of the atoms by volume what does that expect? If they're solid balls and we expect them to all come shoot other balls at them, but they don't, what does that tell us the atom actually mostly is? Not air, empty space. Empty, maybe write the letter T correctly, space. Mostly empty space. So then his model, Rutherford's model, sorry. It also showed us that those that did bounce back was because the nucleus has a positive charge. So there's a positively charged nucleus, mostly empty space, and then he said orbited by, in fact, you've probably seen this. The Rutherford model, maybe it's because of its artistic beauty, is sometimes represented the most frequently by people who don't know anything. But he died just orbits of electrons, kind of solar system. That's the Rutherford model. Mostly empty space, positively charged center, and then electrons spinning around it. I think it was, and you can look this up, and I'm not claiming this is true, but sometime either before or after the Rutherford experiment, after both the proton and the electron had been discovered, the neutron was discovered by James Chadwick, I think. I have to look that one up. But the neutron was discovered last. Why do you think that is? Why do you think the neutron was discovered last out of the three? Yeah, no, because it doesn't have a charge. We discovered the electron by virtue of its charge. We discovered the proton by virtue of Right. Have mass. And so the mass was told us that there must be another massive particle that is contributing to the mass of the proton without contributing to the electrical charge. I think it must say the man's name. Yeah, Chadwick. James Chadwick, 1891 to 1974. All your book says is that showed that the nucleus also contained another subatomic neutral particle called the neutron. So your book doesn't go into depth onto that experiment. And then later, a man called Bohr, and this gives us the Bohr model, using quanta of light, which is certain discrete amounts of light, showed that the electrons actually exist in energy levels. So we still have a positively charged nucleus, but now, instead of the electrons kind of randomly orbiting, they have specific energy levels, which we represent. I'm going to call this one 5 positive, and we're going to have 5. Just that they have discrete areas in which the electrons can exist, and they don't really very common way to represent, especially for when we're doing work with the arrangement of electrons. We use this model still today. This is probably the most frequent way to actually. Well, that's not how it is in real life. We know it doesn't look like this, but that's not the point of a model. A model allows us way. So we still probably use it than anything because it shows where or what the energy levels of the electrons are. And by the way, what's in the Bohr model, current model? What's in the nucleus? What subatomic particles are in the nucleus? Yeah, protons, which have what kind of charge? Positive charge. And what kind of mass? Say it. 1 what? You remember? AMU, atomic mass unit. And neutrons, which have no charge and a mass 1. And those are both approximate. I think the proton is very slightly lighter, or very equal number of varies slightly heavier. I can't remember off the top of my. But they aren't the exact same mass, but we do just usually say they are 1. And then what is out here? Electrons, which have a negative charge, you remember, and no mass. And that's not exact, because that they have 1, I think 1840th, the mass of the proton and the neutron. Around all intents and purposes, chemistry. There are electrophysics. We really do use the mass of the electron quite often. But in this level, especially of chemistry, we really just consider the electron to be massless. So the protons and neutrons are in the nucleus, and they both, what's special about the protons and neutrons? Do you remember they both have mass, and so we add those together and we get the mass number of a specific isotope. And remember that an isotope is a specific arrangement of neutrons and protons. We do express it like this. For instance, this one we could call, if I'm going to call that, it has 5 protons, and we'll say it also has 4 neutrons. We'll call this one boron 9. This is the isotope notation. The element is boron. What does that tell us? How many protons? The name of the element tells the mass number, not the mass, there's a difference. The mass number, which tells us is the sum of the protons and neutrons, but if we know the number of protons is 5, because we know it's boron, and we know that the mass number is 9, we know there must be 4 neutrons. So the mass number is the sum of the protons and neutrons, and then remember, in a neutral atom, the protons and the electrons are equal. If it's not a neutral atom, protons and electrons, what do we call that? It's not even. If there's an electrical charge, we call it a ion. We call it an ion if the protons are not equal to the electrons. And of course, it's a positive ion if there are more protons, and it's a negative ion if there are more electrons. I shouldn't have phrased it that way. I should have said it's a positive ion if it has lost electrons, and it's if it has gained electrons. That's what it is. It doesn't gain or lose protons in chemical reactions. Would you be able to find the number of protons, neutrons, and electrons for a given isotope? It's review from physical science, but do you think you would be able to? For this test. And then the other expectation mathematically is that we're able to do yep. I think your test is limited to alpha, beta plus, beta minus, and gamma radiation. There may be electron capture on there though. But the way that we do those, if you remember correctly, is that we have, for instance, say that uranium-238 undergoes alpha decay. It will release an alpha particle and also, well, let me express it this way. Remember, an alpha particle has the atomic number of a helium nucleus, which is 2, the mass number of 4, and a charge of 2 plus. So if that leaves the nucleus, remember, if an alpha leaves the nucleus, then we have reduced the I think I've written it correctly, haven't I?
I have no idea.
I have. 4 to 234, and now also the atomic number. So now it's thorium 234. Practice with those two. An alpha particle, and you can go back and watch the videos on this to be more in depth. We have alpha, beta plus, beta minus, gamma, which is also, that's capital gamma, electron capture, and spontaneous fission. And all of these things have their own specific mass, charge, and they all respectively affect the mass of the difference, the charge, et cetera, et cetera. This table is filled in and it is filled in your book. The reason I'm leaving it there is because this should be a review. We will talk more about it. We'll do some practice with it. But do you have questions as to how to do nuclear equations? The question wasn't for everything about how to. What?
How do you do that?
That's not a specific question.
How did you get thorium?
Because the atomic number for uranium is 92. Let me write that in. We don't always have to write it in, but we have. I will here. 92. It had to reduce by 2 because the alpha particle is left and it has an atomic number of 2. And so now what's left is 90. And so since the only has 90 protons, we know that it's thorium. Well, it depends. Like, for instance, the given for this one would have been, it would have just said uranium 238 undergoes alpha decay. That's all it would say. Undergoes what the alpha particle is, and then what's left over. You end up just reducing the decay mode is. We can do it now. What's the mass of both beta plus and beta minus particles? You remember? 0. Remember, is a one is plus. Gamma has no mass and no charge. Capture is a little bit, or it's a little bit different, maybe not spooky. It's a little bit different because instead of releasing something to the nucleus, it gains something. So remember, we put electron capture on the same side as the parent particle. And this terminology should be familiar with you, but even if it isn't, we will do more practice with it. But it has a mass of 0, and its charge of itself is -1. But since it's adding to the nucleus, that reduces the atomic number. And then, oh no, it could be not. No, it spontaneously fizzes. Just let me neaten this up a little bit. Oh, I don't know. That doesn't. I'm sorry. That's a typographic error. They can all be expressed either way. I think I'm forgetting something.
So what's the difference between, like, if we get electron capture and beta minus?
Yep. So remember that electron capture actually has the same effect as beta plus because it's absorbing into these two would. If it was the same, this doesn't ever happen. The same parent isotope undergoing the same daughter product. These have the same effect. I'm pointing at electron capture and beta. Because this releasing, actually what's happening is in this one, neutron becoming a neutron, and the nucleus is eliminating, it's ejecting a positive charge. And in this one, it's absorbing of electrons. So they're different methods. They work differently in nature, but they have the same mathematical effect on the daughter product. And the answer to your question, some isotopes undergo this one, and it will tell you. Imagine there might be a question like, Uranium-238. If there was one either, I don't do that. But if that did happen, just choose one and you're wrong, I guess. That doesn't happen. I specifically avoid doing that on this hand, mathematically. Okay, yeah, let me write the name next to it. In fact, that seems reasonable. Alpha, beta, plus. What particle is released from beta plus? Positron. Positron, which is an antimatter particle of an electron. This one is the electron, and that's called beta minus. It would have been easier if I just done this all from the beginning, I'm now realizing, but I was kind of trying to sign, so this was good. I hope it wasn't too confusing. A gamma, which is gamma, but it's not a particle, it's a wave, it's a form of light. It's a particle to the extent that light is a particle, but it is a ray of light. And then electron capture, and then this one is spontaneous fission. Let me make sure that I have you know your vocab, right? I would say other than vocab, that should be pretty much everything. There may be a few things that I've forgotten, but you will read your book. Do you have specific questions about, and maybe not the math about it because we will talk more about that in person, but do you have questions about the nature of radioactive decay and how this works in general? No. Do you have questions about how to find the number of protons, neutrons, and electrons in a given isotope? No. Okay. Do you have questions? The Dalton are the ones that you have to. Do you have questions about any of those or the way they are? Or even, I think there's a couple questions on your test about what experiment showed those. Do you have questions about any of that, how it works conceptually? Is basically coming up with the word atom is what he did. Okay. Okay. Thank you.